Okay, so I think we should start. This. Okay, I've started the recording. Cross check. Cool. Okay, so welcome everyone. My name is Jafar, and I'm a PhD student at the Department of Electrical Engineering. Uh, in the Department of Electrical Engineering at IIT Patna, and I'm my specialization is control systems. So I'll be doing the TA of this course, Control Engineering, which is taken by Professor Ramakrishna Pasumarthy from IIT Madras. And it's our first week. Basically, you would have gone through the lectures and the slides that were shared with you. And mostly, will not be going in details like about the concepts. Rather, we'll only be focusing on the numericals here. I don't know. There is something wrong with this. Why he's not able to join? Okay. Anyway, so in the first week, uh, yeah, cool. So in the first week, what you have learned about different types of systems. For example, you have learned about causal and non-causal systems. Similarly, you have learned about linear and nonlinear systems. And time variant and time invariant systems. Time variant and time invariant systems. So if you are given a system, how can you identify whether it's a causal or non-causal system, it's a linear or non-linear system, or it's a time variant or time invariant system? You have learned about the concepts. Here we'll be solving only focusing on problems, and accordingly we'll be clearing your doubts, if any. And after that, we'll be solving problems on these questions. And after that, you have also studied modeling, right? So how you will, uh, if you are given a system, how you can model that using mathematics, right? And then in the modeling, you have learned how you can transform a mechanical system into an electrical system. There are different forms of doing that. You have learned force voltage analogy, and accordingly, you have learned force current analogy. Correct. Uh, so these things we'll cover. We'll cover with these different types of systems, and after that, there's different types of modeling and how to model. If you are given a mass stamper system or any other mechanical system, how you can model that in electrical domain and using force voltage analogy or force current analogy. Correct. So now let's start with the questions. Question one: if you are given a system with output as yt, which is equal to x squared t plus xt minus 3, right? So you're given a system whose output is yt and input is xt, and you have been asked to find whether this system is causal or not. So you have to find whether this system is causal or not. Correct? So in the lectures, you have learned that in a causal system, the output is only dependent on either the present or the past values of input and not on the future values of input. So if our output, if it depends on the future values of input, then the system is non-causal. So how we check whether a system is causal or not? We start putting in values of time. For example, if we put t is equal to 1, then what happens? We get y of 1 is equal to x square 1 plus x 1 minus 3, which is equal to x square of 1 plus x at minus 2. Correct? So what does it mean? It means that my output y at 1 is dependent on my input at 1 as well as my input at minus 2. So my system output at t equal to 1 is dependent on my present and my past values. Okay, so for the time being, as of now, it should be causal, but we have to check for other values. We have to check for other values of uh, time. So then we check on negative values. Let's assume t equal to minus 1. So y of minus 1 is equal to x square of minus 1 plus x of minus 1 minus 3, which is equal to x square of minus 1 plus x of minus 4. Again, so it here it depended on past and present. Here as well, past and present. Now checking at 0. So t equal to 0, then what should be my output? It should be x at 0 plus x hat will be x minus 3. Correct. So again, my output, it depends on only the present and past values. Correct. So in this case, when my output, it only depends on present and past values of the input, then the system is called a causal system. So therefore, this is a causal system. Why? Because my input is my output depends only on the values of input uh, which are received which are already received. Correct. So they can be present or they can be past. We'll start with easy problems and then accordingly we'll build up. Sorry. Okay, I need to admit all. Okay, so now moving to question number 2. If you have doubt at any time, please interrupt me. So question number 2 will be my yt is equal to x of minus t square. Okay, so can anyone tell me whether this is a causal system or a non-causal system? Accordingly, we'll solve. On the same pattern, on the same pattern uh, on which we did the earlier
Sir,
problem.
sir,
Yes.
your video is not visible, sir. I mean, screen is not visible, sir.
Are you sure? Are you sure? Is it visible to
Yes, sir.
others?
Yes, sir. Is it visible, sir?
It's visible.
Yes, sir.
Okay,
I
so
couldn't see your content, sir.
uh, but others are able to see. So can you maybe log off and then again log in?
Okay, sir.
Okay, you please log off and then again log in. And if there is problem with any other student, please let me know. Okay, now is it visible, Vijay?
No, sir. Maybe I think the issue on my side, sir. I don't think I am not able. I am not able to see, sir.
I have you joined on mobile or a phone? Yeah, laptop or system.
I joined in mobile, sir.
That's why maybe you're unable to log like uh, with the correct uh, tab probably because it's Teams, so it's a bit complicated than Meet and other platforms. So anyway, please try. Maybe uh, it is visible. So okay, coming to this question. So can anyone tell me whether this system is causal or a
Yes, sir. Now
non-causal
it is
system?
visible, sir. Yes, sir. Thank you, sir.
Okay, okay,
It
cool,
is visible, sir.
cool.
Thank you, sir.
Yeah, okay. So should we solve it? Can anyone comment? We'll
Causal.
obviously
Non-causal.
solve it.
Causal.
Causal. So
Non
who is saying
non
causal?
non-causal.
Okay.
Non-causal.
Udaya Kumaran is saying non-causal. Okay. So somebody is saying causal, somebody is saying non-causal. Let's check it. So again, we'll check at different time instance. So again, one important thing which I forgot to tell you is that these systems where I'm mentioning T, they are continuous time systems. So they are taking all values, right? But we have another class of systems where okay where which are called as discrete time systems where the system it takes discrete values, correct? So and again, okay, let's check. So solution, let's check at t equals to 1. So at t equals to 1, what's the value of y? What's the value of y? It is x raised x minus 1. So it depends on past here. So no problem. As of now, it should be causal. Then we'll take t equal to minus 1. So y of minus 1 is equal to x of minus 1 because minus 1 square is 1. So again, it depends on past. Then we'll take t equal to 0. So when we take t equal to 0, what will it be? It will be x equal to 0. So present, correct? Then what's the problem? So as of now, okay, wait a minute. As of now, it looks like the system is causal. But as I said, we have to check for all values of time. Since we are only checking on integer values because they're easier to check, but we need to check on other values of time as well because they are continuous time systems. So let's check at t equals to be 1 by 2. So what will be y at 1 by 2? My y at 1 by 2 will be x minus 4. So here, this is y of zero point 0.5 and this is x of minus 0.25. So it depends on my output, it depends on past. So no problem. No problem as of now. Still causal. Again, let's try at minus 1 by 2. So my y at minus 1 by 2, it is equal to my x at uh, minus 1 by 4. So here my y is 0.5 and here my x is minus 0.25. Now here if we see, it's a negative. So my output at minus 0.25, minus zero point 0.5, it depends on the future values of input x. So here this future comes. So you have to be very careful. You have to be very, very careful where you check, but only check at these 5 points. 1, minus 1, 0, 1 half, and minus 1 half. Correct. So At any point, if you see it is coming on future, no need to check. It's non-causal. So here the system is non-causal. Why? Because y at minus y at minus 0.5, it depends on x at minus 0.25, which is greater than point. Wait, I'll admit all. Okay. So this system is non-causal. Now again, moving on. Another question. Now we'll take a discrete time system. Let's assume, as of now, we took two continuous time systems. Now we'll take the same system, but my my output y of n is equal to x of minus n squared. Now, can anyone tell me on what values we have to check here? Can you try? Can you try and tell me whether the system is causal or not causal?
Causal.
You can try. You can try. Yes.
Non-causal.
So who is saying non-causal? I couldn't see.
Non-causal.
Kiran.
Non-causal.
Okay. Okay. So whoever is saying non-causal, can you please elaborate on what value of n it is dependent on future?
-1/2.
But again, what I told you is that this is not a continuous time system. This is a discrete time system. See, when I took, this is the same system, see, yt is x of minus t square, but here why I took n and why I chose the notation of brackets. So this is how we represent a discrete time system. So in discrete time system, see, for example, I'll explain here. Let's assume I have a continuous time system x whose input, sorry, I have a continuous time system whose input is x and output is y. Then as I vary x, I get some value of y, for example, like this. Correct? So we can say, let's assume this is 0, this is 1, this is 2, this is 3. Okay. So we can say that our system is taking values from 0 to 1, any value between 0 to 1. And there are infinitely many numbers between 0 and 1. And our system is taking value on, taking out, like, is getting output on all those values. But contrary to this, if we have something like this, we have a system where x is this input, and this is 0, this is 1, 2, 3, and 4. And our output is like this. Sorry, this is 1. Then on 2, we have this output. On 3, we have this output. On 4, we have this output. Correct? So our output will something look like this. Right? This is not continuous. This is not continuous. Okay, I'll explain you. It's not continuous. So our output is taking values at discrete time intervals at 1, then at 2, then at 3, and then at 4, so on. It can also take values like this. This is 0, this is 1, 2, 3, 4, 5, 6. It can take values maybe at 1, then at 3, right? Sorry, not like this. It will take values at 2, at 4, at 6, so on. So why I made this two different graphs for discrete time systems to show you that there is a concept of there is a concept of sampling time, right? So we will only get outputs after that particular sampling time or sampling period. So in this case, my sampling time is 1, and in this case, my sampling time is 2. So I'll get my output after every 1 second, let's assume. And here I'll get output after every 2 seconds. But we're not getting the outputs continuously. For example, you are standing on a road, and like it's not a busy traffic there, right? So it's not busy traffic there. So cars will come or vehicles will come. One vehicle came. Then after 2 minutes, another vehicle came. After 30 seconds, another vehicle came. After 5 minutes, another vehicle came. So vehicles are not coming continuously. Then you will not be able to cross the road. So vehicles are coming at a discrete time interval. That can be fixed, that can be constant, or that can be varying. So, but vehicle cannot come here. So in my continuous time case, we were checking our system at fractional values as well. For example, we checked at half and minus half. But discrete values, it's easier for us to check on integer values, right? So in discrete domain, you will always remember. Somebody has not muted, so can I mute? Mute. Okay. So in discrete time, when you have discrete systems, you always check only at three times. Like for example, n at 1. What will be my n at 1? Y1 is x of minus 1. So my output is dependent on past values of input. Then at n equal to minus 1. So at n equal to minus 1, my output is dependent on present. Then at n equal to 0, when I have n equal to 0, then I get x equal to 0, present. So in this case, my system is a causal system. My system is a causal system. These are very basics, and you will learn, or you might have learned these type of questions in your signals and systems course. So this week is basically a very basic course, a very basic introduction about the systems and about modeling. And then as we keep covering this course, and we'll be delving more into the actual control system stuff, right? So this is a causal system. Now another question, the same question. Y of n is equal to x of n square. Now, can you tell me whether this is causal or not? Very simple
Non-causal.
example. Okay, good. So can you tell me why? So it's a non-causal system because if you plug in n equal to 1, what will we get? Y at 1 is equal to y at 1. So it depends on present, no problem. But if you plug in minus 1, so y at minus 1 depends on my x at 1. So my present depends on future. So obviously it's not. And at the moment, when you get your system is dependent on future values of input, then there is no need to check on other values if you are being asked whether it's a causal or non-causal systems. So clearly we need not check on other values. So this system is a non-causal system. Now, a very, very important question. Sorry? Pardon. Okay, I'll mute participant. Yeah. Okay. So now, can you tell me this system y of t is equal to x of mod of t? Can you tell me? You take time, don't rush, be very sure. I told you, you have to check. This is a continuous time system. So you have to check at t equal to 1, t equals to -1, t equals to 0, t equals to half, and t equals to minus half. At any moment of time, you find your system output is dependent on future. No need to check. No need to check for other values. Straight away, it's a non-causal system. So take time, take 1-2 minutes. And then on the same grounds, y of n is equal to x of minus mod of n. Now, tell me for both these systems, whether our system is causal or not. Okay, let's try. So at t
Both are
equals to
causal.
1, great. Okay, so both are causal, we'll check. We'll check one by one. So at t equal to 1, what will we have? Y at 1 is equal to x at minus t at 1 is 1, so it's 1. So it means the dependency is passed. Correct? Now at y equal to -1, what will be the value of -1? Again, it will be passed because mod of anything which will come out from mod is positive. Similarly, we have y0. Y0 will be x of 0 is passed. Y half is x of minus half, again passed. Now, important one is this one, y of -1/2. What is y of -1/2? It is x of minus
Minus
1
1
by
by
2. So what is it? It is present, right? No problem. Now let's
2.
check this system.
T of
So this
-1
is,
is present, sir.
yeah. So I wrote
But you
present here.
passed
No, I
T
wrote
of minus.
present. Oh, sorry. T of -1. Thank you. Now let's jump to the other one. We only need to check at T1, T-1, and T0. Correct? And here I will get y of 1 is equal to x of -1. Here I will get y of -1 is equal to x of -1, and y of 0 is equal to x of 0. This is a causal system. Correct? Okay, I'm admitting all. Now, one more question, one last question. We'll do on causal and non-causal, and we have a lot of questions to do. One last question is y of t is equal to x of e raised to the power t. So can you tell me whether this is a causal system or a non-causal system? Okay. Ramya said non-causal. Very good. How? If we put t equal to 1, what will we get? Y of 1 or y1? We will put no need. Y of 0. What is y of 0? X of e raised to the power 0. It's equal to x of 1. So my present is dependent on future. So this is a non-causal system. Correct. So causal systems are those systems which are present, like the output of which depends on the present or past values of the input. And if the output depends on the future values of input, then our system is a non-causal system. The details, the explanation of this all you have learned in your lectures. Correct? Now
Sir, I
coming to
have
the
doubts, sir.
yeah, sure.
Sir, please don't mind me, sir. I am I didn't understand this basics, sir. Sir, y is a function of t, right, sir?
Uh,
Here again, why
yes.
we have equated to another x is an equation. X is a function of e of t.
Okay.
Why
Okay.
we write like that, sir?
Okay. Actually, this is like uh, like you are saying y is a function of t, then x again is a function of t. In other
Ah, yes,
examples,
sir.
there was this. There's see y is a function of t, x is a function of t, or t square, whatever. So it is just the it's just the time step at which we are seeing the response of the system. For example, imagine like this. You have a system. You have a system like this. So this is output, this is input. And what we are doing here, we are saying at any point of time or at any point of time, if my input, this is input, any point of input, just like this or this, they are at different time steps. So this. So we are saying at that particular input value, how my output evolves. Like, is my output depending on future values of input, right? Don't confuse with time. It's actually, yeah, it's actually the we are considering it with respect to input values. Input values, like see, input is also a function of time, output is also a function of time. So we are saying at what values of input our output, like what is the relationship of our output with the input values. So both are dependent with time. Now again, we will see in a short while time variant and time invariant systems. So for example, you have learned in the lectures, if you perform Ohm's law, if you perform Ohm's law today, you'll get V is equal to IR, or V by I is constant R. And if you perform Ohm's law tomorrow, you'll again get the same relationship, right? So you perform today and tomorrow. This experiment, it didn't vary with time. So irrespective of when you are performing the experiment, you get the same relationship. But if you see time varying system, whenever we talk of time varying system, we talk with respect to parameters. For example, you are riding a car and you started from here. Now you went 10 kilometers. So when you started, let's assume you had 2 liters of fuel. And when you drove to 10 kilometers, you're only having 1 kilometer, 1 liter of fuel. So your car is a time variant system with respect to the parameter fuel. Correct? So we'll come to that. We'll come to that again. But as of now, don't confuse like it's a function of this or then why we are taking it like that. Just focus whether our system is dependent on present values of input, sorry, whether our output is dependent on present values of input or uh, what are we getting? Are we getting it is dependent on future values or it's dependent on past values? And these all systems, they have specific applications. For example, you're forecasting weather. right? So you don't know that in advance. So that's a non-causal system. Correct. So you have learned this. You have learned this in your lectures. Correct. So we have a lot of questions to do today. So let's keep on going. So another type of system classification is linear and nonlinear. I'll just so again you have studied linear systems. They follow the principle of superposition and homogeneity. Correct. So, but how to check whether a system is linear or not? We again have some rules. We again have to check, right? So, for example, if we take question number one, we have a system whose output is x of t plus 5. Now, we have to check whether the system is linear or not. There are many tricks to solve this question, but since you're learning it, maybe most of you would be learning this course. They would be having this course in their undergrad studies, and others may be preparing for GATE or whatever reasons. But uh, when you are learning the course for the first time, it's always better to learn rules because tricks you can apply at any time. So I can straight away tell whether this is a linear or non-linear system. But it's better to go by following some basic rules. So in order to check whether a system is linear or not, we have to follow a set of rules. Number one is we give input x1. For example, if we give x1 as input, what will we get? Y1 as output. So y1 of t is the output which I will get when I give input as x1. Correct. Now, if I give x2 as input, what will I get? I just have to replace this input. So if I give x2 as input, so I'll get y2, which will be nothing but sum of like x2 plus 5. Correct? So in order to check whether it's a linear or nonlinear, you have to do this. Now, what is the third step? You have to add them. So y1 of t plus y2 of t. So adding them, so we'll get x1 of t plus x2 of t plus 10. Correct? I'm naming it equation 1. So what have we done? We have a system yt is equal to xt plus 5. We are giving an input of x1 and seeing the response, which is coming out to be y1. Then we are taking another input x2, getting a response y2. Correct? Then we are adding them. We are adding y1 plus y2. Now we will give another input x3, which will be the sum of x1 plus x2. So we will give another input, which will be x1t plus x2t, x1t plus x2t. So let's assume I'm naming it as z of t. So now I'll add this input here. So what will I get? I'll get y of t is equal to z of t plus 5, as I did with other these things. I'm taking another input, but zt is x1 plus x2. So let's name this as y3. So y3 of t is equal to x1 of t plus x2 of t plus 5. We'll name it as equation 2. Now we have to compare equation 1 and 2. In equation 1, we gave how we got equation 1. We gave input as x1, then we gave another input as x2, then we summed them, summed the responses. In y3, what we did, we gave a combined input x1 plus x2 and saw the response, which is y3. So on comparing 1 and 2, we found we can see that they are not equal. So y3 of t is not equal to y1 plus y2. So the combined effect, it's not equal. Why? Because here we have plus 5 and here we have plus 10. Correct. So they are not equal. So it means additivity fails. So linear system follows this property that uh, uh, if I give input at equal to 1, T1, and then another input at equal to T2, then if I give another input, that is T1. If I give combined input T1 plus T2, then I should get the output as Y1 plus Y2. So here I should have got Y3 equal to Y1 plus Y2, but I'm not getting Y1 plus Y2 because here I have 10 term, here I have 5. So clearly this additivity fails. Additivity, that is superposition. We know that linear systems, they follow the principle of superposition and homogeneity. So when additivity fails, we can right away say that this is not a linear system. But again, sometimes let's assume this additivity is satisfied. Then what we have to do? We have to check for homogeneity, right? So what is homogeneity? So again, what we had a system yt is equal to x of t plus 5. Yeah, I think we have the same system. Yeah. Now, what is homogeneity? Homogeneity means if we scale our input, we should get, that should not impact our output. Correct? Like we should get the same output. So for example, I am scaling the input by a. So what should I get? I should get a xt plus 5. So this is my input. This is my output when I am scaling my input. My input. Yeah, this is my output when I am scaling my input. Scaling. Now, second thing, what we have to do. So we started with this for homogeneity. We started with this. We scaled our input. We got this. We got this equation. Now, with this equation, we have to multiply both sides by a. This is a check. This is a way to do it. So we multiply a on both sides. What we will get? We get ax of t plus 5. Sorry. So we get this term. So now we have to compare. We have to compare whether these two are same or not, right? Clearly, we can say this is 5a and this is 5. Again, homogeneity is also not satisfied. So this system was a nonlinear system. We could have directly said that after checking the additivity property, but we again went for to check whether the system is satisfying homogeneity property. But again, we found that system is not satisfying the homogeneity property. This will be again clear in another example. Let me take another example where it will be more clear. For example, yeah, this example. Y of t is equal to x of sine t. Correct? So if we see this example, whether this is a linear system or a non-linear system, we have to check for both additivity as well as homogeneity. So for additivity, we'll take x1 as input, then x2 as input, then their combined effect, and compare with whether we are getting the same input if we add them or not. So y1 of t is x1 of sine t. Correct? My y of 2 will be x2 of sine t. Third step is to add them. What will I get? Y1 of t plus y2 of t is equal to x1 sine t. Sorry. Plus x2 sine t. Okay. Now I am giving x1 plus x2, x1 t or x1 and x2 as combined input, x1 plus x2, right? I'm giving this combined input. So what will I get? Y3 of t is equal to x1 plus x2 of sine t. Correct? So what is this? x1 sine t plus x2 sine t. So what does it mean? Y1, so it means my y3 of t is equal to y1 of t plus y2 of t, where my y3 is taken at x1 plus x2. So this is satisfied. It means my system satisfies additivity property. So we have to keep on checking whether now my system satisfies homogeneity property as well. So for homogeneity, we had the system y of t is equal to a sine of, we had the system y equal to x sine of t. So what we have to do, we have to scale the input by a. So y of t, it will be a x sine t, correct? This is one equation. Now again, for this equation, we have to multiply the output by both sides by a. So what will we get? A x sine of t. So we can say they both are equal. So the system follows homogeneity principle. Homogeneity holds. Here additivity holds. Therefore, my system is linear. Correct? So now, based on this, can you check? It's a very, very important question. So if you are able to solve this question, you have understood linearity. So can you check whether this is linear or non-linear? So now, based on this, can you check whether this system is linear or non-linear? Take your time, take 2 minutes, solve it. Okay. Y of t is mod of x of t. Whether this is linear or non-linear. Again, let me try to solve it. So we will start with y1 of t. What will it be? Will be mod of x1 of t. And y2 of t, it will be mod of x2 of t. Then we'll add them. Y1.
Non-linear.
Great. So who is this? Who said this? Can you come again? Who said this system is nonlinear? Okay, no problem. So y1 plus y1 of t plus y2 of t is equal to x1 of t plus x2 of t. So as of now, there's no problem. Yeah. So as of now, there is no problem. Now we have to take another input. Now we have to check at another, we have to check the combined effect. So what will be the combined effect? The combined effect will be x1 of t plus x2 of t. Now tell me whether y3 is equal to y1 plus y2 or not. Now tell me. Yeah, anyone?
No, sir.
Yeah, because we can evaluate this. We know that mod of a plus b is less or equal to mod of a plus mod of b. Correct? So clearly we can see that 1 is not equal to 2. Therefore, additivity fails. Now, what about homogeneity? What about homogeneity? Again, I'll do it for you. Y of t was x of t, mod of x of t. Now, what we have to do, We have to scale the input by A. So scaling the input by A means we have to do like this, correct? Let's assume it, I'll name it 3. Then in the fourth step, what we have to do, we have to multiply A both sides of this equation. So I'll get ay of t is equal to a x of t. Now tell me whether they imply to each other. Now tell me
No,
whether,
sir.
No, sir.
sorry, how, why they are not, we can take it outside, why and they're not, this is not, they are not equal. See, if we take a equals to be 1 here, then what we will get? In the first case, we'll get yt is equal to, since a is positive, so it will come out as positive as well. So it will be 1 of x of t. And same holds. So let's assume it's y1 here. So y1. And here again, it will be, if a is 1, it will be 1 of x of t. Then they are equal in this case. But take a as negative. So if we take a as negative, we will get positive out from the mod. So again, if a is negative, y1 of t will be x of t. That's if a is -1. Again, then we'll have y1 of t as xt, but let's assume it is y2. Let's assume for the time being. Then y2 of t will be minus of x. Minus of x of t. So clearly y1 is not equal to y2. So for negative values of a, this homogeneity doesn't hold. So in that case, our system is nonlinear, correct? Okay, jumping towards other types of systems. Can take a break of 1 minute. So any one of you has like, is anyone among you from second year of BTech? If any, please raise hands. Oh, Rishika is second year BTech. Rishika, can you please unmute yourself and tell me which college are you from? Oh, there are many people from second year BTech. So PES, what is PES? I don't know. So you can unmute yourself if you're comfortable. Okay, your mic is not working. Got it. Okay. So, okay. So there are two guys from second year. So you can lower your hands. So anyone from third year of BTech? Because accordingly, we have to see, we have to keep everyone going. We have to make it. I know there must be many people here who know already these things, whatever I'm doing, but for the sake of other people, we have to do it like that. So nobody from third year, anyone from fourth year of BTech? Siddharth. Okay, so okay, you are from fourth year. Fourth year, many people from fourth year. Okay. Okay. So anyone not doing BTech, doing some basic course or some other coding courses, you can lower your hands. Devanand and Siddharth, you can like lower your hands now, or maybe I can do it for you. Your hand. Okay. Okay. So coming to another class of systems, that is time variant and time invariant systems. Again, a very important class of systems, because in whole this control course, mostly you'll be focusing on linear and time invariant systems. So you'll be, or maybe you might have heard this term, LTI, linear system. It could be linear system, so it will be following the principle of superposition and homogeneity, and it will be time invariant system. So as I said, if you perform Ohm's law today and tomorrow, that doesn't it doesn't matter. So it doesn't matter when are you performing in time, the output has to remain the same. Correct. So now if we have to check, uh, if we have a system, let's assume we have a system S, and we give uh, an input x of t, so accordingly we'll get a output of y of t. But now if we delay, if we give delay by t naught, then if we are getting that delay in the output as well, then it's a time invariant system. Correct? So for example, there is another way, like when we checked the causality and non-causality of systems, we put in some values for time. Then when we checked linear and non-linear systems, we checked homogeneity and superposition. And again, when we have to check the time variancy and time invariancy of the systems, we have to follow some rules, a very, very simple rules. So question number one, let's take question number one. That is yt is equal to t of xt. Solution. So we have to find whether this system is time variant or time invariant. So how to check whether the system is time variant or time invariant? There are different methods. So I'll tell you a simpler one. So first of all, what you do, you delay this system. You delay xt by t naught. So that is what you'll do. You'll replace xt by x of t minus t naught. Correct? Then what will I get? Output yt will be t x t minus t naught. Correct? So I delayed x by t naught. I'll name it as equation 1. Then in the second term, you will replace t by t minus t naught. In the second, this was first step. In the second step, you replace t by t minus t naught. Then what will we get? We get y of t minus t naught is equal to t minus t naught x of t minus t naught. So if now we have to check if if these two equations, if they are equal, then the system is time invariant, or if they are not equal, then the system is time variant. So again, if we check 1 is not equal to 2, therefore the system is time variant. This will be clear in another example. Let's take some example which is time invariant. Yeah, I'll take question number next, which is y of t is equal to x of t plus 1. So solution, first step, delay x of t by t naught. Sorry. So when you delay x of t by t naught, what you will get? Yt is equal to x of t minus t naught plus 1. Correct? Now what you have to do, you have to replace, second step, you have to replace t with t minus t naught. So what will you get? You will get y of t minus t naught is equal to x of t minus t naught plus 1. So clearly we can see it from here. 1, this is 2, 1 is equal to 2. Therefore, the system is time invariant. Correct? We'll have quickly some more examples. Now, can you tell me now this question is y of t is equal to x of t plus 10 plus x square t. Now, can you tell me this system? Sorry. Now, can you tell me this system, whether this is a causal, oh, sorry, it's time variant or time invariant system? Anyone? Anyone? Whether this, you can take your time, whether this is time variant or time invariant system. Our first step is
Invariant.
invariant. Great. So our first step is delay x by t naught. So what will we get? We'll get y of t is equal to x of t minus t naught plus 10 plus x square t minus t naught. Then second step, I will directly write, replace t by t naught. We will get xt minus t naught plus 10 plus x square t minus t naught. Correct? So this is again a time invariant system. Right? So another important question. Y of t is equal to x of 2t. Now, can you tell me whether this is a time variant or time invariant system? Now, this, tell me, this is a time
Yes, sir.
variant. Time variant. Who said time
Yes,
variant?
yes, sir. Time
Evan.
variant system.
So, can you explain others how this is a time variant system? So, if we replace t, if we delay time, delay x by t naught, what will we get? Can you repeat? So, okay. You have to be very, very careful. So, when we delay x by t naught, what will we get? We'll get x of 2t, then minus, then what will we get? 2t naught or t naught? What
2t
will
naught.
we get?
2t naught.
Who said 2t naught? No, I nowhere said. So in that case, it will be like this. X of 2t minus t naught. So it means we are delaying whole, like we are delaying 2 as well. I nowhere said to delay this thing. I only said to delay t, to delay x, right? So x of 2t minus t naught, right? So we'll get this. Then if you replace t by t minus t naught, so it will be t minus t naught, it will be x of 2. Now it will be t minus t naught. Now it will be x of 2t minus 2t naught. So you have to be very careful. It's now a time variant system. This was the trick here. You just don't have to delay. You just have to delay the x, not constant as well, right? Now, one more example and then we'll wind up. One last example. One last example. This I would like to get answer from you guys. If I have the following system, y of t is equal to t x of 2t plus 2. Now you have to find whether the system is option A, linear, time variant, causal, option B, linear, time invariant, causal, option C, non-linear, time variant, non-causal, correct? And option D, linear, time variant, and non-causal. Right now, check whether the system is which of the following options holds for the system. Okay. Tell me. Tell me which of the following holds for it. I'm coming. Now tell me which option is correct. D. Somebody is saying D. So who is saying D? Check. Ramya. Ramya is saying D. Anyone who wants me to solve this question, please raise your hands if anyone wants me to solve this question, or you'll take it as your homework, because we have solved a lot of questions.
Sir, option C.
Okay, so you are saying it's a nonlinear system, right?
Yeah.
Uh, okay, so did you check? How did you check for linearity? What is not like is superposition, is the system satisfying superposition principle or not? Okay, let me check. So option C and option D are same, but only difference is option C says it's a nonlinear system and option D says it is a linear system. So okay, let me solve it in any case. Solution. You can lower your hands, whoever has raised your hand. So check for causal or non-causal system. If we put t equal to 1, what will we get? We will get y of 1 is equal to 1 and x 2 plus 2. So straightforward, we got present dependent on future. So clearly this is a non-causal system. No doubt here. Now, linear or non-linear, we'll check. Because if we check linear, non-linear, that it will be easier for us. So for linearity, what we'll take? We'll take y1 of t. So what will y1 of t be? Y1 of t will be t of x1 2t plus 2. Similarly, y2 will be t of x2 2t plus 2. Then y1 plus y2, it will be t of x1 2t plus 2 plus t of x2 2t plus 2. Correct? Now, what we'll
What
give,
will
we'll
you?
give combine. Sorry, please mute yourself. So now what will we give? We'll give combined effect. Correct? We'll give combined input. So when we will give combined input of x1 plus x2, what we will get? We'll get y3 as t of, then here it will be x1 first, then x2. Correct? So it will be x1 2t plus 2 plus x2 2t plus 2. So does that mean y3 is equal to y1 plus y2? Yes, clearly if we multiply this, then we can see y3 is equal to y1 plus y2. So the system is linear, and I'm not checking for time variancy or time invariancy, because with these two things we can say the system is time variant, and that is left to you as your homework. Now, since we have less time, we have to cover other things as well. So now we'll go towards the modeling part. Modeling part is very, very important. So you have read in your lectures force current analogy and force voltage analogy. Okay. So I'll briefly recall. So modeling of mechanical systems, or why we do force voltage and force current analogy, because we want to learn mechanical systems in terms of electrical systems, because we are very well familiarized with electrical systems. Correct. So if we have a mechanical system like this, if we have a mass spring damper system like this, so if we have a mass spring damper system, please mute yourself, whoever has not. This is M and this is Ft, and we are assuming it's a rigid body. So this will be x of t, displacement when we apply force. This is spring constant K, and this is viscous friction damping. So I hope you are well versed with these things. So if you have to model this system, like uh, there must be some equation governing this system. So we need to write that. So we can clearly see that Ft, this is the force acting on this body. And when this force acts on this body, because of Newton's law, we have this mass moving, then we will, with some displacement x, then clearly what we'll be having is this F of t is m into a, but I am writing a in terms of displacement. So m d2x by dt square plus b dx by dt, b into v. B normally comes into v because there will be friction. So it's I am assuming that you already know these things. So now what we got? We got this equation of this mechanical system, that is Ft is m d2x by dt2 plus b dx by dt plus kx. Correct? So this is a second order differential equation. Right. Now, in force voltage or force current analogy, what we do, we represent this system in an electrical system. We make an analogy that this system can be represented by an analogous electrical system in two ways. One is by taking force as voltage, by making this analogy that force is voltage, and by making another analogy, which is the second one, which is by thinking of taking force as current. So now see this thing. If I make a series LCR circuit, correct? So this is V of t, this is R, this is L, this is C, correct? There is some current I of t going inside this circuit. Now, if I have to write Kirchhoff's laws, what will it be? So I'm naming this equation as equation 1. Now, writing equation. So this voltage, Vt is equal to voltage drop across R, this inductor, voltage across this inductor, and voltage across this capacitor. So this Vt will be R into It plus L di by dt plus 1 by C integration of I dt. I hope these things are very, very clear to you. Now, can we make this assumption since we know that this I is equal to dq over dt charge, we know this current is rate of change of this charge, then we can modify this equation. Vt is equal to R, not writing, I'll write, if this is dq or dt, then this will be L d square q by dt square plus R dq over dt plus q over c. I'm naming this equation as equation number 2. Now, if you compare equation 1 with equation 2, and if we take F as voltage, then my mass will be, if F is taken as voltage, then my mass will be replaced by, my mass will be replaced by inductor L, and my displacement will be replaced by charge. My B will be replaced by R, and K will be replaced by 1 by C. I hope this is clear. I hope these things are very clear to you. So when we are modeling the mechanical system using force voltage analogy, then we have force as voltage, mass as inductance, displacement as charge, damping as resistance, and K as 1 over C. Correct? Now again, so this is one way of writing this system in an electrical analog system. But there is another way, which is, for example, if we make a parallel RLC circuit. So we have a current source I of t, then we have, it's very important for you to solve questions. Correct? So we have voltage, maybe V, then this I, it splits into, this is R, this is L, this is C. Quickly I'm writing the equation for this current IT. It will be V over R plus 1 by L V dt plus C dV by dt. If we replace V as d phi by dt, Faraday's law, then what we will get? It implies I of t will be C d2 phi by dt2 plus 1 over R d phi over dt plus phi by L. Again, so this is another equation. If we want to model that system using the force current analogy, then when force is modeled as current, we have mass as capacitance, B as 1 over R, and what was the other equation? K. K as 1 over C. K as 1 over C. Anything else left? Yeah, phi becomes X. So this is a brief overview of force current and force voltage analogy. So now for the same system, if you are asked to draw
K 1 over L.
the, sorry,
For K 1 over L, right, sir?
1 over L, sorry. Yeah, thank you. So these are just the expressions. So these are just the expressions. If you have to draw, if you actually have to draw these circuits in using force voltage analogy and force current analogy, how you can draw that? See, I'm just copying this system here. See, so you have this system, and to make things easier, we do a bit of simplification here using nodal method. So how we can redraw this method, how we can redraw this mechanical system into electrical system, there's a way to simplify it, correct? So that method is called as nodal method. Like we do nodal analysis, that same method is called nodal method. Please be attentive. So now you see on this system, we have one displacement, X, right? So we'll mark this displacement here. One displacement is there. We'll mark this displacement and you will mark ground reference. So there's one displacement and ground. So you will start making this diagram like this. So one displacement is there, and this mass M is connected between this point X, like it's connected between this X and ground, correct? Now what else we have? We have a spring constant and a damper also connected from this mass to the ground. So we have a spring. We have a spring connected from this, and we have a damper also. Correct. And what else do we have? We have a force acting on this mass. So we have a force F. Sorry. We have a force F of t acting on this mass. So this is a complete diagram. So this is M, this is K, this is P. Correct. Now you have to solve this. You have to write analogs equations, and you have to write, since we have already written that equation, that mathematical equation for the system, but I will again show you when we have complex systems, how we can write these mathematical equations first for this mechanical system, and then transform these circuits into force current and force voltage analogous circuits, right? So how we have to write using, since I again said it's a nodal method, so we'll apply nodal analysis like we apply in circuits. We have this force at this point. We can say force is coming here, it's going here and here, like, and here, correct? So what we can write? We can write this f of t as m d2x by dt plus b dx by dt plus k x. Now, if we have to make a force voltage or force current analogy, what we have to do? Again, for force current analogy, make the same circuit, make the same circuit. So I'm making the same circuit for force current analogy. Only I have to check the values, correct? So this is F, this is M, and we know that this is for force current analogy, this B is replaced as This 1 by R, correct? So B will be replaced as 1 by R. So uh, it will be B actually, because we are not making an electrical circuit. We are just writing it. So it will be 1 over B, and for K, 1 over L. So 1 over K, right? Sorry, I made the same circuit, but we have to make force, current, and all the circuit. Wait. So in a force current analogy, mass is replaced with capacitor. So we have to make a capacitor here, correct? But on the same use in the same diagram. So I have to make a capacitor here. Then this spring is marked with inductance. Spring is marked with inductance, right? And this damper is marked as resistance, right? So this is a force current analogous for this system. It will again be very clear. I'll make this is will be m units of capacitance, and this spring it will be 1 over k. L will be 1 over k, and this will be 1 over r, 1 over b. Sorry, because units will be same. Now, what we have to do for force voltage analogy? Force voltage analogy, since we have two nodes here, we have one node here. So this will become a mesh. So one node will become mesh. And this now for force voltage, we have to make dual of this circuit, right? So how we'll make dual of this circuit? So in order to make dual of the circuit, whatever connections are connected in series, they are connected in parallel, right? And inductor will become capacitor, series will become parallel, resistance will become 1 by R, correct? So when I have to make the force voltage and analogous circuit for this will be voltage. So this will be a voltage source here, plus minus. F of t is a voltage source now, correct? Then after this, we have these three elements in parallel. They will become in series. In mass will be replaced by inductance, correct? Uh, so sorry, this capacitance will be replaced by inductance, correct? So we have an R for this, right? And this inductor will become capacitor. This capacitor will become inductor. So it's one and the same thing, correct? So it will be mass. This will be mm, B oh, Henry, and this will be plus minus capacitance is 1 over K, correct? So this is X and minus X here, right? So these things will be more clear. I'll just explain this in another example in a bit detail. If we have a system like this, now for this system, we have two masses, X1 and X2. This is K1, this is B1, this is B2, this is K2. So if we have to make First of all, if we have to write the equations for this system, for this mechanical system, like how we have to write it, using nodal methods. So we have two displacement here. We have two displacements here. We can see x2 and x1. So we will mark these displacements. Let's assume this is x1. Let's assume this is x2. Correct? Now we have, with this x1, we have this mass m1 connected, this mass m2 connected with ground. Correct? So now what we have in between mass m1 and m2, we have k1 and b1, right? So in between mass m and m2, we have k1 and b1. Correct? So this is k1, this is b1, right? Now what else do we have? We have
Sir,
b2
I
and
have doubts.
k2. Yeah.
Sir, M2 is
Yes.
connected to the ground by P2 K2, no, sir. But M1 is
No,
not
no.
connected to the reference.
I'll wait. So m2 is connected to ground. Here, I'll show you. Now tell me. Is there any problem?
But in the question, M2 is connected by in above drawn, sir, roof.
Yes, this one. What is happening? Yeah, m2 is connected to.
To the top one, no, sir, B2 and K2. It
Yes.
connected to the reference, no, sir. But M1 is not
Yes.
connected directly to the reference, no, sir.
But how is it possible? Like uh, they are connect. You are saying this is not connected directly with the reference. Why am I connecting it directly with the reference, right? So
Yes, sir.
in nodal method, we start with this assumption that we start with the displacements and all the masses, they are connected to ground. Correct. This is just a way of representation. And if you find the equation of this using free body diagram and this equation, it will be exactly the same. Correct. See, in your case, the forces on this M2 will be because of this B1, because of this K1, and because of this K2, and because of this P2. Correct. So there is no reference. M2 is not reference node here. But if you check the equations which you will write and the equation which I will write, they will be exactly the same. The only advantage is that it's very simpler. Whatever I am doing, it's very simpler. I'll show you. See, so what else is left? We have only this force which is left here. Now see, we have M1, a force being applied to M1 here. Then we have K1 connected between M1 and M2, K1 connected between M1 and M2, B1 connected between M1 and M2, correct? Then we have M2, then we have B2 connected to ground and K2 connected to ground, correct? So this circuit is, this is B2, sorry, this is K2 and this is B2, this is B1, K1, M1, correct? Now I'll show you how easy it is, rather than using this free body diagram. See, if we have to write equation, you will come nodal analysis, just apply nodal analysis. Come on this point, force is coming here, it will go here, something here and here, correct? On this point, it will be like this. So how we can write equation? First, for this first node x1, we will write f of t is equal to m1 d2 x1 over dt2 plus b1 d by dt. Now we are writing with reference to node number x1, but this b1 is connected between x1 and x2. So we have to incorporate the effect of x2 as well. So it will be b of x1 minus x2. Correct. Similarly, it will be k1 of x1 minus x2. So very simple here. Done with equation number one. Now equation number two on this node, right? So on this node, there is no incoming. So we can write 0 is equal to m2 d2x2 over dt2 b2 because of this b2 dx2 over dt2 plus k2 x2 plus now this is left, this k1 is left, so this will be the effect of b1 and k1 is left, so it will be b1 d by dt of x2 minus x1 plus k1 x2 minus x1. So is it clear? So when writing nodal analysis, I took node x1 and node x2. I applied this KCL at node x1. F was equal to m d2 x1 by dt2. Then b1, since b1 is connected between x1 and x2, I wrote as b1 dx1 minus x2. Similarly, I wrote the KCL for this another equation, another node, right? So these are the equations governing the system. But now if we have to make the force current analogous circuit and force voltage analogous circuit, how we will make it? This is very interesting. I think after drawing force current analog systems for this, then you will be able to draw for any other system. See, for force current analogy, we will draw the same circuit, just replace mass by inductor, right? Mass by inductor, because other we have to follow this for force voltage analogous things. Sorry, force current. Mass will be capacitor, right? So for force current analogy, mass will be capacitor. So we have to remember this. Rest everything will be same because see, K is inductor here and K is capacitor here. So if we are modeling mass as capacitance in force current analogy, then in force voltage analogy, we will use mass as inductor, right? So just making the same circuit. So for force current analogous circuit, what we will do, we will make a force Ft. Then see here, we have mass, right? So mass will be replaced as capacitance. So mass will be replaced as capacitance here. Then we have a spring and a damper. So we have an inductor and a resistor. We have an inductor and a resistor. Correct? Then what do we have? We have another mass. So we have another capacitor. Correct? Then what do we have? We have another inductor and another resistor. So we have another inductor and another resistor. So I made the same circuit. If you see, I made the same circuit, just changed mass and this K with inductance and capacitance. So this is force current analogous circuit. And then again, you will put the values. This is M1, this is M2, this is 1 over K2. You'll just put on the values. 1 over B2, 1 over K1. You just check them whether these values are correct or not. like just comparing the values. Correct. Now this was force current analogy. So whatever mechanical circuit you have, from here you draw the nodal, using nodal analysis you make this circuit, this reduction. Then on the same circuit just replace mass with capacitor, so you'll get force current analogy. Now using this circuit we will draw force voltage analogous circuit. How? We will make a dual of this circuit, right? Nodes become mesh, right? Parallel connections become series and vice versa. Correct? Inductor will behave as capacitor. Like not behave, we take that. Like in order to make. Now see, this is connected between node 1, node x1, and node x2. So since in force voltage analogy, we will be having meshes. So we have two nodes here, we'll be having two meshes here, and they are connected in parallel. So we will connect them as series, correct? So inductor will be replaced as capacitor. So we will replace this as capacitor and then series in resistance. So they were connected between x1 and x2 here. They will be connected in parallel because they will form meshes. Correct. Now this mass is capacitor. It will be changed into inductor. It's connected in parallel. It will be connected in series. So here this mass will be inductor connected in series, and here we will have the force F of t. Now what do we have? We have a capacitor and inductor and a resistor connected in parallel. Correct. So they will all be connected in series, but inductor will be converted into capacitor will be connected into inductor, but we have two, so no problem in that. So we'll write an inductor, a resistor, and a capacitor here, right? So this is B1, right? So this is 1 over K1, this is M1, M2, B2, 1 over K2. Correct? So this is mesh 1. This is mesh 2. Correct? Anyone has any doubt here? How we draw this force voltage analogous circuit from a force current analogous circuit, or how we draw this mechanical circuit using this circuit? Or can we do another example and then maybe things will be more clear? Let's do another example. Let's make it a bit zoomer.
Sir,
So
in
let's
the
take.
duality circuit,
Uh-huh.
current source
Yes.
can be converted to voltage source, no, sir?
Sorry. In the dual circuit.
It is, I think, voltage source, no, sir?
Yeah. Oh, sorry. Thank you for this clarification. So this will be a voltage source. Very good. So now let's do another question. Very simple question we'll do, just to make things more clearer. Right. So we have this damper and we have this spring. Then we have this M2. Then we have another damper. Then we have M1. Here we have F of t. Then here we have X1. Here we have X2. This is K. This is B1. This is B2. Now again, I'll not waste time. So if we are solving it with nodal method, what we'll do, we will define two displacements and a ground. Correct? And connect masses with those two displacements, right? So if I mark this as x1 this as x2. So this will be then M1. This will be M2. They both are connected to ground. So I hope this is clear. So now what do we have? We have in between M1 and M2, we have a damper. We have a damper. So in between M1 and M2, we have B2, correct? And in between uh, M1 and ground, we have a B1, another damper. I could have drawn it here, but there is no space, so I'm drawing it here. There's no problem in that. Correct? So this is B1. Then here I have force F of T. Anything else with M2? Yeah, we have a K2. So is this clear how, like, this is very simple method to draw. This is M2, this is K, this is M1, B2, B1, and force. So in order for you to draw force current analogous circuit, what you have to do? You have to do nothing, just replace mass with capacitor, right? So see, in order for me to draw a force current analogous circuit, I'll draw a current source like this. Then this is a resistor. Then this is a capacitor. Then here we have another resistor. Then here we have another capacitor. Then here we have an inductor. Correct? So this is M2. This is M1. This is 1 over B1 FT. This is 1 over B2 X1 X2 K1 over K2. Correct? So is this clear? This is very simple how we just replaced mass and other components by their respective symbols. Correct. Now, in order for us to draw the dual of this system, what we have to do, see, again, there are two nodes. So for force voltage, we will make dual of this. So there are two nodes. There are two nodes, X1 and X2. We'll have two meshes, uh, mesh 1 and mesh 2. This resistance is connected in series between X1 and X2. So we will have it connected in between mesh 1 and mesh 2 in parallel. Correct? Then what we have, what do we have? We have a resistance and a mass connected in parallel. Correct. Sorry, we have a capacitor and a resistor connected in parallel. We will have an inductor and a resistance connected in series. So we have an inductor and a resistor connected in series, right? So B1, this is M1, and here we have, oh, yeah, we have a voltage source F of T. Then what do we have? We have a capacitor in series. We'll get an inductor in. We have a capacitor in parallel. We'll get an inductor in series. And again, for this inductor, we'll have a capacitor in parallel, right? So it will be 1 over K2. It will be M2. And this is mesh 1. This is mesh 2. Is this clear now? Is it easier? Is it easier now? Anyone has any doubt? So using this method, now you could see that it's very easy to write these equations rather than making a free body diagram and then writing forces, balancing forces, because you're already well versed about this nodal analysis. So it's always better to make use of that and solve the question. So if you have understood, so we can solve another interesting problem. So it's like this. It's like okay, so we have a mass M2, a spring connected to it, and ground, a damper connected to it, and ground. This is K2, this is B2. Here, this is X2, right? And we have another mass, M1. And then we have a spring connected in between and a damper connected in between mass 1 and mass 2. This is K1. This is B12. There is this force being applied in this direction, M1. This is X1. We have a damper also connected to this M1 and ground. So see, I could have made this damper like this again and taken here. So there's no problem. This is again ground, this is ground, so there's no problem. So this is the question we have, and we have to write the using nodal analysis, the equivalent, the circuit for this, and the consequently the differential equations governing this system. Right. So again, I will start with the same, in the same way. We have two masses, x1 and x2, m1 and m2, correct? So this is reference here. Now, what do we have? In between M1 and M2, we have K1 and K2 connected, right? So we have in between M1 and M2, we have K1 and we have B12, correct? Now with M2, we have K2 and B12. So M2, we have B2 and K2. Correct? So we have B2 and K2. And for M1, what do we have? We have a damper. That's it. So we have a damper. I can draw it here. I can draw it here. No problem. So I have a damper. Then I have a force acting on this mass. Correct? This is B1. It's probably B1. Yeah, this is B1. Then M1, K1, B12, M2, B2, K2. Done. We are good to go for writing the differential equations for the circuit. Again, we will write this f of t at this node x1. So f of t, it will be m1 d2x by dt square plus b1 dx1 over dt dx1 by dt plus. Now we have two components here between x1 and x2. One is k1 and one is b12. So we have b12, then d by dt of x1 minus x2, because we are taking with respect to x1, and plus we have k1 x1 minus x2, if it is k1. Yes, it's k1. So we are done with node number 1. Similarly, at node number 2, we have 0 is equal to m2 d2x by dt square plus B2 and K2 we have, so B2 D2, sorry, dx over 2 over dt plus kx2, correct, plus B1 to d by dt of x2 minus x1 plus k1 x2 minus x1. Is it clear? Anyone has any doubt? Will you be able to write differential equations for these systems now, for such systems? Yeah, anyone has any doubt? So can you write the force current analogous circuit for this system? What we have to do? Just replace this mass by capacitor, this B by resistor, this mass by capacitor, resistor, and inductor. Then again, by making analogous circuit, when making dual of this force current analogous circuit, sorry, force current analogous circuit, when we make dual of that, then this will define. So this inductor and resistor, this inductor and damper, they are connected in parallel. So we will have a capacitor because of this uh, inductor and a resistor because of this damper. Then since they are connected in parallel, they will be connected in series. So for this element, we will have something like this when we'll be drawing dual. Then then with that in between, we'll draw. It's very easy. I hope you are getting that. Just before finishing, there is one question in the practice assignment. I hope now that will be very easy for you to solve. Before I end, just quickly, I make sure that you're able to solve this question. This is K2, this is K1, this is X, and it's shown that we are acting force on this. F is force, and this small f, this is the damping. This is actually the damper. So this is uh, uh, like the damper which I used to make. Right. So it's actually this, right? It's disconnected. So of value f. So now can we make the nodal using nodal method? Can we make a circuit for this? Very simple. We have a node 1 x, then we have mass m1, sorry m, that is connected to ground, correct? Then in between ground and m, we have this k1 and k2. Both are between. Don't get confused, there are two separate grounds. Ground is the same thing, right? K1 and K2. Then what else do we have? What else do we have? We have a force F acting, and we have a damper. We have a damper which is written as F. Correct? We have a damper written as F. So that is shown because of the direction you should be able to find, because this mass, there will be some friction, and because of that this damping will take place. So now would you be able to write the equation for this? So it will be F equal to m d2x over dt2 plus k1x plus k2x plus f dx over dt. Is it clear? Is it clear now? So whoever had asked the question that why we are not, the mass is connected in between not directly to ground, why we are taking it ground. Now, is it clear how easy it becomes to solve for these systems,
Yes, sir.
right? Yeah, so it's very easy. I hope things are clear. Just uh, as a homework, I'm giving you one question. Just try that and tell me next time that what was the answer. Like, this will try check your concept, right? Everybody, just make with me because we are running out of time. Just try this because if you are able to solve this question, then you will be able to solve any question based on this force, voltage, and force current analogy. M3, B3, K3. We have X3 here. Then again, we have K2. We have another damper, B2. We have another mass, M2, with a displacement of X2. Then here we have another damper, B1, then a mass M1 connected. So here it will be X1 to this mass, a force F is acting. So this is B2, this is K2. Again, what do you have to do? Write the differential equation governing this system using nodal method. Also make force current and force voltage analogous circuits. Is the question clear? Is the question clear? So for this system, you have to write the differential equations that govern this system and using nodal method, and also you have to find the force current and force voltage analogous circuits. So first you will make the differential for the differential equations, you will apply nodal method, you will get some mechanical equations that and then on same equations on the same model, same circuit, you'll just replace mass with capacitor and other things, and you'll get force current analogous circuit and make the dual of that. Whatever is in series, make them in parallel, change capacitor to inductor and inductor to capacitor, vice versa, series in parallel, parallel in series. So things will become easier and you'll be able to get the dual of the system, which will be the force voltage analogous circuit. Correct? So any doubt here? I'm just concluding this session here. Just stop. Thank you very much, everyone, for attending. If anyone has any doubt, you can just post here, or I'm just stopping the recording. So thank you.
Sir, can we get the recorded videos, sir?
Yes, they will be shared.